crack Maxwell's equations, step 1. Now, the first equation we talk about is Amperes law in the Maxwell's equation form. Okay, so what is Amperes law is you have current density and the change of electrical flux. This we talk about this later. Let's say we concentrate on current density equal to curl H, or some of them use rotation H, or inverse triangle times external vector product. Okay, so that's a Maxwell's equation, and we will have a profound understanding on what this equation is telling you. Okay, now we can use the math to get the integral form of this Maxwell's Amperes law. Means we take an integral on the area of the current density. So suppose you have a current going, the density divided by area. Okay, so all the current we take integral, then that's what this means. So taking a surface integral of H vector is like orthogonal. You take a integral is same as line integral along the path. So this is L and this area is D. Okay, so this is just a math problem. The taking integral along this closed loop is going to give the total integral of surface on J. Okay, so what does this mean? Well, you can tell the current density and the magnetic fields are related, right? So that means magnetic field causing current density, or current density causing magnetic field? Well, this equation actually it's a one way. The current density is generating magnetic field. That's what it means. And how the current density generate the magnetic field? Okay, it's a rotation. If you examine carefully the rotation definition, curl, whichever you call, you have current density going, the current density vector. The rotation, that means it's going to be right hand law. So that's where the Amperes law come from. The magnetic field is a closed loop around the current density. So current density generate this kind of magnetic field B or H. So this is right hand, you have a thumb pointing J, then all the magnetic field is the remaining fingers. Okay, and Amperes right-hand law is result of this, the math expression, the curl H. So the relationship between them is in this equation. But you know what? Then when you know the J, how do you take an integral? We don't know this H, how much H is generated. Okay, is it the function of distance? Yes. Okay, so what is H? This equation doesn't tell you anything about how the H look like. which is generated by the current. How do we figure out? Okay, and that's what you have to understand in this section of the Maxwell's equation. You know the relationship H and J, and you know what is the cause and effect. J is a cause and H is the effect. Okay, but this equation doesn't give you how to obtain H for a given J. So we go back a little bit. The Gauss equation, divergent E equals rho over epsilon, and this E is defined as the potential gradient. Okay, so we have a Poisson's equation. This is equivalent to square, and that's details given here. Okay, Poisson's equation is going to give the relationship between potential and charge. Remember this? Okay, so this is a differential equation. If you solve this differential equation with boundary condition, then you get, when potential is given, it's easy. Take a derivative, you get distribution of the charge. If distribution of charge is given, then that's going to be harder because you have to integrate to get potential. Once you get the potential, then you can get electric field, right? So same way, we hope somehow we find out the potential and source of the magnetic field. This guy, J, and some kind of potential, magnetic potential. So once we find out, then we can use exactly the same way like a Poisson's equation, solving Poisson's equation. Now we also know that this Poisson's equation's integral form, we developed this in a textbook, the integral form of Poisson's equation. If rho, in this case m, there's no true charge for the magnetic, it's only dipole. And dipole, when the dipole is given, we can calculate potential, magnetic potential, right? You take a integral. Then by taking a gradient, we can get magnetic field. So if the source of magnetic field is dipole, we already know how to calculate how much magnetic field we get. Then in this case, the source is not dipole, it's J, the current. Okay, so remember, divergent B equals 0, right? So this is one source. The charge, when charge is a source of magnetic field, this is the equation, and this lead to Poisson's equation, and the Poisson's equation lead to the integral form, and then we can calculate how much B is generated. Okay, but magnetic field has a second source. This is a second source, which is J, the current density, and that's what Maxwell's telling you. The Maxwell's first two equations, divergent D and divergent B, they are talking about the charge, electric charge or magnetic charge. But magnetic field can be also generated by another source, which is J. That's what Maxwell's equations means. Okay, when J is a source, what we do is we define some kind of potential, and the way we define the potential has to be vector potential. Okay, vector potential, nothing difficult. It's just a potential with each direction. So you have a 3 component in the vector potential, a little bit more complicated, but same thing. Vector potential, we define curl A. Okay, so we put that in. So curl B equals curl A, and that's become negative. Let's see. Okay, so exactly like the potential Poisson's equation. Okay, because gradient divergent A is 0, so we get this Poisson's equation. It looks like this is the magnetic charge. Okay, and Poisson's equation look like that. But here we have a vector potential. Vector potential A is for the current density. So we break it down to each component and use the same method to generate the integral form. And so this is the integral form of the Poisson's equation for potential vector. And you know, once you get this, this gives the E. Same thing, once you get A, then what you do is give you B, right? So we use the same thing here, right? And in this equation, there is a current I, and we have a coordinate origin, and point of interest is R, and the distance from here to element of current density is Q. So this is gonna be R. So R equals Q plus R. Okay, so it's just a vector expressions. You can change to coordinate. The bottom line is we can get B equals 1 over 4 pi, and just integrate I. It's a component of at the point Q. Okay, and external product of gradient so this is gonna be R vector dV. Okay, so we get actually the how to calculate magnetic field generated by current. Okay, so we use simplified form. Suppose this element of I, we treat it like M, right? So then you get the dipole is going this way, exactly same effect. The equation is same. Okay, then we can simplify this equation to Biot-Savart law, which is for the element of dl, right? This is the dl. Integrate current, then we get magnetic field. So Amperes law, J produce B, and what kind of B is produced? This is the equation. Okay, this is the cause and this is the effect, and we have a mean to calculate this. What kind of B is generated by J? It look like reverse proportion to square of distance from every element. Okay, so it's just a matter of integrating it. So here Poisson's equation give you this how to calculate, how to obtain H. It's just all the math manipulation, but this equation, Maxwell's equation itself, doesn't give you any idea how to get H, and it doesn't give you which one is the cause, which one is the effect. That's what you have to know. This is the cause, this is the effect, and how much H you get, the method of calculating is given by all the way vector potential and B, and simplified format, which is Biot-Savart law. Okay, so that's what you got here. Now once you know how much B is generated, right? So you know the M generate this much B. Suppose you have a element of current and it's look like a dipole. Okay, then we know already the force is going to be this equation. That is called Fleming left-hand rule. Okay, Fleming left-hand rule come from here. The treating J, element of J is like a magnetic charge, and interaction with B, if there is a B running this way, so it's going to interact. So it's all explained from above to down here. So a simple application, like a motor, right? When current flowing the loop, voltage V, okay, so dF is going to be IDL times B, and F is going to be IDBN. So this is a force, and when this almost flip, we change the polarity of this, then it keep spinning. Okay, and this is called a DC motor, and DC motor is like widely used by, you know, the disc spinning devices. And if you increase number of magnet and coil, you can control precisely how much angle you rotate. Okay, that's a DC motor. Okay, so far Maxwell's Amperes law is starting with this equation. Now we got the source of magnet, not only magnetic charge. Magnetic charge is, you know, magnetic stick. You have a charge here. Not only magnetic charge, current also give a magnetic field, and that's what this Maxwell's equation is telling you, right? This is a cause, and this is the effect. Okay, how it's generated, it's just like you use Poisson's equation to solve it, but this time the potential energy is vector potential energy, not the potential you learn in the first two Maxwell's equation. Now there is a third source of magnetic field, which is this guy. We promise we talk about this later. Okay, this is like the flux time change. So what is d flux time change? Okay, the d flux time change is like a capacitor, right? And Q accumulate on both sides. So d dt represent the current, right? The current going to the capacitor. So what's happened? Well, the flux time change is considered as equivalent as current and cause magnetic field. So if you make a device like this, what's happened is you have a flux going and flux change around because it's alternate voltage source. So this is the time function. So electric field change around, right? Okay, and this flux change, because it's a Q minus Q, change to Q and minus Q. Okay, this flux change generate magnetic field orthogonally. That means electric field generate magnetic field. Okay, so what happened is this, if you make this, consider this oscillation, then electric field go up and down and magnetic field generate orthogonally. And it's propagate, it become wave. This is a EM wave, and we talk about this in step 3. Before we go there, we have to talk about next Maxwell's equation, which is Maxwell Faraday's law. The Faraday's is basically magnetic field generate electricity. Well, cause is magnetic field, and the result is the electric field. So it's go opposite. Okay, Maxwell cover both sides. The J generate B, and B generate back the E, which is ultimately cause J, and this counter J, it's a negative feedback. Okay, so Maxwell's equation tells you that Maxwell Amperes law go this way, and Max Faraday's law goes the other way, and both always happen. When this happen, and this gonna make sure this happens. So there is a negative feedback loop here. And if you understand that, you pretty much understand Maxwell's equation. This is a very deep understanding of what the Maxwell equation is about. Okay, so this is step 1. I hope you like it, and please check step 2, and if you like, subscribe.